Felicitations, the internet, and happy 4th of July. I just dropped a video on a mathematical proof of the product rule. So for the sake of reciprocity, I am going to now drop a video on a mathematical proof of the quotient rule. The quotient rule can be written as follows. That is, the derivative of the rational expression u of x over v of x equals u prime of x times v of x minus u of x times v prime of x all over v of x squared. So in other words, the derivative of a rational expression, some function over another function, is the same thing as the derivative of the function that's in the numerator times the function that's in the denominator minus the function in the numerator times the derivative of the function in the denominator all over the function in the denominator squared. All right, so let's try to write out a mathematical proof for the quotient rule. This comes in many forms. All right, so these are the exact same thing. Personally, I like this one because, well, it shows that u is a function of x and that v is a function of x, and well, it doesn't have Leibniz notation. It's not that I have a problem with Leibniz notation. Leibniz notation is fine, but one is a lot cleaner than the other. But for simplicity, as this takes up a lot less room, we're going to use Leibniz notation, and we're just going to use the variables u and v, and not showing that they're a function of x, but just know that they are a function of x. So I'm just going to get rid of this, and we want to show the quotient rule. We want to prove the quotient rule. So we want to show that the derivative of u over v is the same thing as v times the derivative of u minus u times the derivative of v all over v squared. All right, so suppose that we change x to x plus the change in x. We know that u and v will also change. U is going to change to u plus the change in u, and v is going to change into v plus the change in v. So that means that u over v is going to change to u plus the change in u over v plus the change in v. So taking this all into account, we can write an equation that shows the amount of change. We could say that, well, the change in u over v, well, that's going to equate out to be u plus the change in u, and what we could say for as for the denominator, that's going to be the same thing as a v plus the change in v, minus u over v. So we have this equation here, and ostensibly we're supposed to find the difference between these two rational expressions. But the issue is we cannot find the difference between these rational expressions unless they have a common denominator. So we need to find the common denominator. In this case, the common denominator between these rational expressions is going to be v times v plus the change in v. So I'm going to rewrite out this first term, that is u plus the change in u over v plus the change in v. And in order to get our common denominator, I need to multiply both the top and the bottom by v. So as for the second term, u over v, well, this is going to get multiplied by v plus the change in v on both the top and the bottom. So really what we could do is we could take this and we could put this into one fraction since the denominators match, and we can actually combine the numerators. So all I'm doing is I'm just combining our numerators. Okay, and then in the denominator, well, it's just going to be our common denominator. At this point, we can go ahead with some distribution. We're going to have in the numerator v times u plus v times the change in u minus u times v plus u times the change in v. The denominator is just going to stay the same. And when we look at this, we can see that positive v times u is going to cancel with negative u times v all day. So we're done with that. Those cancel out. So I'm just going to clean this up a bit. I'm going to write that the change in u over v, well, that's going to equal v times the change in u minus u times the change in v all over v squared plus v times the change in v. I just went ahead and distributed that v in the denominator there. If we take this and we divide it by the change in x, and then multiplying and dividing the change in v term in the denominator by the change in x, well, we're going to get something that looks like this. That is, the change in u over v over the change in x equals v times the change in u over the change in x minus u over the change of v over the change of x all over v squared plus v times the change in v over the change of x times the change of x. All right, so now let the change of x approach 0. We got the change of x approaching 0. Better yet, let the change of x approach 0. If we let the change of x approach 0, all of the fractions are going to become derivatives, and the final factor on the bottom is going to go to 0. So, as it turns out, we're going to end up with the following. That is, the derivative of u over v equals v times the derivative of u minus u times the derivative of v over v squared plus v times the derivative of v times 0. But since this last term in the denominator here is being multiplied by 0, this whole thing here, this last term, is going to go to 0. And since the last term in the denominator here goes to 0, that means that we just proved the quotient rule. The derivative of u over v equals v times the derivative of u minus u times the derivative of v over v squared. This here is the quotient rule, as shown above. Special thanks to Adrian Banner. Cool book, bro.